Hello, I hope you're all well. The following lecture will cover sections 1.1 to 1.5 in the text. It will be handy if you have a periodic table. You can print out the periodic table on the course Blackboard page in the supplemental materials folder. Section 1.1 is just an introduction to organic chemistry and sort of why we're studying this. The course is organic structure, which will be the focus, but 1.1 is just a brief introduction. Organic chemistry is simply the study of carbon-containing molecules and their reactions, and we're really only going to be dealing with a handful of elements, unlike your general chemistry course, which dealt with the entire periodic table. We're going to be dealing with carbon, nitrogen, oxygen, sulfur, phosphorus, and a few of the halogens. And that's basically it, with that focus on carbon-containing molecules. So organic chemistry is a very significant branch of chemistry in that it affords us an understanding of all living systems. Organic molecules are the backbone of or building blocks of all living systems. But we also use organic compounds for clothing, pharmaceuticals, plastics, which are polymers, and all food is made of organic molecules. The study of organic chemistry is broken into several branches. It is a vast field, but if we break it down into three sort of boxes, we can look at organic chemistry from a structural perspective, a mechanistic perspective, and then there's synthetic organic chemistry. Our main focus is going to be on structure. However, we will be looking at mechanisms and we will be looking at synthesis. Section 1.2 deals with the structural theory of matter. Much of this you'll have seen in your general chemistry course. So a chemical substance is defined by its arrangement of atoms and its formula. Isomers are simply compounds that have the same formula but are different in a particular way. There's a variety of different isomers that we'll be covering this semester. The first of which is a constitutional isomer. A constitutional isomer they're simply isomers that have the same formula but a different connectivity of the atoms. Constitutional isomers have different properties such as melting point, boiling point, and density. Those are all physical properties, and they also behave differently in chemical reactions. So we say they have a different chemical reactivity. So the first skill is to be able to identify constitutional isomers, and we do that by looking at their formula and then the connectivity of the atoms. Let me give you an example. Let's look at two isomers, both of which have the same molecular formula, C2H6O. We have diethyl ether and ethanol. If you look closely, you can see that the formulas are the same because both of the compounds have the same number and same type of atoms. You can just count them up and you see C2H6 and O for both. However, if you notice, the connectivity of the atoms is different. Look, we have an oxygen that's sandwiched in between two carbons with diethyl ether or dimethyl ether. And then we have the oxygen, which is sort of in between a hydrogen and a carbon for ethanol. Both of these compounds have different boiling points. So that sort of is just an example of how they have different physical properties. Now that we know about isomers, let's talk about bonding basics, which should be familiar from Chem 1. So Because we're going to be dealing primarily with a small number of atoms, we're only going to focus on sort of the top right-hand side of the periodic table and those elements. So you should know from Chem 1 that each element generally forms a specific number of covalent bonds. Now we can get into why and the exact number of bonds that they form later. However, what you should know is that certain groups on the periodic table, if you look at the carbon group, everything, all the nonmetals in that carbon group are typically tetravalent. We say this is group 4 on the periodic table. Tetravalent means they like to form 4 bonds. The nitrogen group, which is group 5 on the periodic table, these elements typically form 3 covalent bonds. You see we have 1, 2, 3, and there's the lone pair or non-bonding pair of electrons, which makes a total of 8 electrons around the atom, but we'll get to the octet rule later. Everything in group 6, oxygen's group, we say these are divalent. These atoms like to form 2 covalent bonds. See, we have 1, 2. Now notice each atom still has 8 electrons around it. It has the octet, but here we have 2 lone pair. Monovalent elements, such as hydrogen, which can only form 1 covalent bond because it has only the 1s orbital in that first energy level. And then we also have the halogens, which are group 7. So hydrogen, group 1, halogens, group 7. And notice the halogens, they still have 8 electrons around them. However, they've got 3 lone pair or non-bonding pairs of electrons and 1 covalent bond, so they're monovalent. We're going to keep these patterns in mind when we begin to draw isomers for a given compound. Now here's a summary of some of the bonding patterns that you're going to see. We're going to focus on carbon, hydrogen, nitrogen, oxygen, and the halogens. Now before we get into formal charges, all right, which is just, formal charges is just sort of an accounting method for the valence electrons. Some atoms have an extra electron, or some atoms have one less valence electron than their neutral state. And we reserve formal charges for those atoms. However, for right now, until we learn how to calculate formal charges, we're going to be focusing on the neutral atoms, things with a formal charge of 0. You should become familiar with these bonding patterns and the valency of each of the atoms. Let's take a look at carbon. We said that carbon was tetravalent. Now, carbon can have 4 bonds in a variety of different patterns. It can have 4 single bonds. It can have a double and 2 singles. It can have a triple bond and 1 single bond, or it can have 2 double. In each case, carbon has 8 valence electrons and it has 4 covalent bonds. And you could go through the same with the valency patterns for nitrogen, oxygen, hydrogen, and the halogens, which all have their own unique set of bonding patterns in their neutral state. Carbon has the largest variety because it likes the most bonds. So keep this in mind. We may have to refer back to this table when we begin drawing isomers. All right, so you might want to read this problem, stop the video. I recommend giving it a try on your own, and then once you think you have an answer, come back and listen to my explanation. So if you've tried this problem, you'll see we need to identify which of the 2 are constitutional isomers. for which are constitutional isomers. Remember, the definition of a constitutional isomer is an atom that has the same formula but a different connectivity. So let's look at the formulas. We have C2, H3, Cl3, C2, H2, Cl4, C2, H4, Cl2, C2, H3, Cl3. Looks like compounds 1 and 4 are constitutional isomers because they have the same formula but a different connectivity of the atoms. Next, we're going to draw 3 constitutional isomers of C3H9N. We're going to assume that all atoms are neutral. So what we're going to do here is try to come up with all of the combinations based on the neutral bonding patterns from a few slides ago. Assuming the formal charges are 0 for each atom, use that table in your notes to try to come up with all the combinations for as many isomers as you can. I believe there's 4. Try to get 3 out of the 4. So go ahead and stop the video and try to come up with as many isomers as you can for C3H9N. And once you're done, come back and look at my answers. So once you've tried these, I'm going to show you all of the isomers that I came up with. So to begin, I typically like to string them. Let's look at number 1. I like to string all of the carbons together and then put any heteroatom or a non-carbon, non-hydrogen atom on the end. So we have 1, 2, 3 carbons in a row, and I put the nitrogen on the end. If we stick to our bonding patterns, we see that, and we fill the hydrogens in, we want to give each of the carbons 4 bonds. So each of our carbons, I filled them in with 4 bonds using the hydrogen. And remember, nitrogen, if it's neutral, it should have 3 covalent bonds and 1 lone pair. So we just fill the nitrogens in, or fill the hydrogens in. It's very important to note that if you drew this with the nitrogen on the left side, it's still the same compound because the connectivity is the same. We just flipped it over like a pancake. You can draw things differently, but in 3-dimensional space, they're still the same molecule. Let's look at the second isomer, number 2. Instead of putting the nitrogen on the end, right, we could string our carbons together and put our nitrogen up top. And then we fill our hydrogens in. To satisfy all the valency patterns, put 2 on the nitrogen, and we put our lone pair. So that would be the process. Now, we also could have drawn this in a variety of different ways. You could have drawn it, put the nitrogen on the central carbon up top, or you could have put that nitrogen on the bottom. In either case, both of these compounds are exactly the same, because if we just flip one over like a pancake, we can overlay it perfectly on the second. Just that it has the same connectivity tells us that it's the same compound. If you look at isomer 3, it's just a different combination. We can put, instead of putting the nitrogen as a branch, we can include it in the main chain. Yet another option, filling in the hydrogens to meet the valency patterns for each of the atoms, for the carbon and nitrogen. And the fourth possibility would be putting the nitrogen in the center. So number 4, you see how we put the nitrogen in the center, 3 covalent bonds, 1 lone pair, and we put our carbons on the outside and attach hydrogens to meet the valency patterns for each of the atoms. Section 1.3 deals with Lewis structures and several terms that you've probably seen from Chem 1. The first is the octet rule. Okay, now we're really going to be using this for second row elements. Other periods or rows on the periodic table can have more or less. However, we're going to focus on the second row elements. So atoms tend to gain, lose, or share electrons to achieve an octet. Okay, that gives them the most stable electron configuration. They can have more or less, but they like to have 8. An ionic bond is when we have a transfer of electrons, that's usually between metals and nonmetals. And a covalent bond is when a pair of electrons is shared between two atoms instead of having an electron transferred. Electronegativity is the ability to attract electrons in a bond. You should know the trend on the periodic table. The trend is up and to the right, being having atoms in the top right with the highest electronegativity. Atoms at the bottom left have the lowest electronegativity. That will be very important. You need to understand electronegativity throughout this chapter 1 material. Let's focus on covalent bonding because it is the primary bond type that we're going to be dealing with in organic chemistry here. Remember, covalent bonding is the sharing of a pair of electrons. So let's look at hydrogen. If two hydrogen atoms come together to form a bond to make H2, right, we get a covalent bond. Now, I assume that you know that this line means 2 electrons being shared, but if you didn't know, now you know. All right, so we have 2 electrons being shared, which is represented by a line in between 2 atoms. Let's look at a potential energy diagram. The potential energy diagram for the formation of this bond between 2 hydrogen atoms. We have bond length on our x-axis, or internuclear distance, and we have bond energy on the y-axis. There's a couple things going on here. We need to understand how does potential energy and stability relate. Well, the more stable the bond, right, the lower the potential energy. So if we take 2 hydrogen atoms that are infinitely isolated, right, there's no energy between them. The energy is almost 0 out here. As we bring them closer together, right, we can try to understand the energetics of this bond. So as the atoms get to just the right spot where the bond forms, let's call this sort of the sweet spot. And at the sweet spot, we know the maximum amount of energy has been released. All right. Bond formation is exothermic, meaning it releases energy. If it's lowering the potential energy, it's becoming more stable. So at the point where the 2 atoms have released the most potential energy, we say that this would be the bond strength, or the energy required to break that bond. It's equal to the energy released in forming the bond. And if we come up to the x-axis, this would be the optimum bond distance. All right, so we have bond length and bond strength. So everything to the right of our sweet spot is where we have attractive forces forming. Everything at the sweet spot is where we have attractive and repulsive forces balanced. And if you smush the atoms too close together where we have a smaller internuclear distance, notice how the energy shoots up. That's because the repulsive forces are being sort of increased. You have two positive charges in the nuclei that are repelling each other. And then the negative charges of the electrons, when they're smushed too close together, also create a repulsive force. Our next section deals with atomic structure, much of which is a general chemistry review. Hopefully everybody knows that the protons and neutrons are found in the nucleus, that the electrons are outside of the nucleus in your electron cloud in the orbitals. The valence electrons are the electrons in your outermost shell. And an easy way to identify the number of valence electrons is by looking at the group number of the atom. So if you look at your periodic table, you might notice that there are different numbering systems. We're going to use this particular numbering system for groups 1 through 8. We're going to ignore the transition metals for now. And if we look at groups 1 through 8, the group number, 3, 4, 5, 6, 7, and 8, and so on, will tell us the number of valence electrons. For example, the carbon group, which is group 4, right? Group 4, so it has 4 valence electrons. If we look at the electron configuration and identify the outermost electrons, right? Electrons in the outermost shell, so the second shell is your outermost shell. How many electrons are in there? 2 plus 2 gives me 4 electrons. If you look at nitrogen, group 5, meaning it has 5 valence electrons. Let's look at its outermost shell. In the second energy level, we have 2 in the S and 3 in the P. So we have 5 valence electrons. Before we begin drawing Lewis structures for molecules, you need to be able to draw the Lewis dot structure for a particular atom. The Lewis dot structure for an atom simply has a dot around the atom, and the number of dots represent the number of valence electrons. So, for example, let's look at boron. Boron is group 3 on the periodic table, meaning it has 3 valence electrons. You draw the element symbol B and 3 dots. Now, we can take some generic atom X, and the total number of spots or slots will be 8. 2 on each side. So that was boron. I like to place the dots around and don't double them up or triple them up on any one side until you absolutely have to. So if we take nitrogen with 5, I would put 1, 2, 3, 4, and then once I don't have any empty slots left on a side, I'll pair them up. Drawing the Lewis structure for a molecule, all right, we can do this in a variety of different ways. Here's the textbook method. You can draw the individual dots to represent the valence electrons, and then put the atoms together so they share the pair, making up complete octets. So this is for very simple molecules. There is a different way to do this, which we can cover shortly. But if you take a look at nitrogen and 3 hydrogens, so that's ammonia and H3, we draw the Lewis structure for each atom. Okay, we have 3 hydrogens and our nitrogen, and we put them together to make shared pairs. Now you can write it with the dots, or you can draw it with lines for each covalent bond, and your non-bonding electrons would be represented by the pair of dots. The alternative method, which I like for simpler molecules, is probably closer to what you learned in general chemistry. You can follow these 5 steps. Now, it's very important that you follow the 5 steps in order. You don't just try to wing it. If you know these 5 steps, it makes drawing Lewis structure for simple molecules very easy. Step 1, count the valence electrons. And make sure when you're counting, if the molecule has a charge, a positive charge means it has lost an electron because it has an excess of positive charge. If it has a negative charge, that means you add one more electron. Step 2, you determine the central atom, that's the less electronegative. Remember, the trend for electronegativity is up and to the right, so the least electronegative will be down to the bottom left, most electronegative top right. The central atom should be the less electronegative atom, and hydrogen will never be in the center. So make a note of that if you need to. Hydrogen will never be your central atom. Step 3, we're going to add remaining electrons to the exterior atoms to satisfy the octet rule. Step 4, if you have any extra electrons from what you totaled in step 1, you can add them to the central atom to give it an octet. And step 5, finally, you may need to use multiple bonds if your central atom does not have an octet. So some important exceptions and things that you need to know. Don't ever draw carbon with more than 4 bonds. Okay, if we're assuming that it's a neutral molecule, then carbon needs to have 4 bonds. It should not have less. It should not have more. Some exceptions to the octet rule. All right, hydrogen can only have 1 bond because it only has 2 electrons in the first shell. Boron typically likes 3 bonds or 6 valence electrons. That's just an exception. So don't use multiple bonds or put lone pairs on borons after it's got 3 bonds. Third row elements on the periodic table, or third period elements, basically anything in the third period or below, these elements can exceed 8 valence electrons. Not that they always will or have to, but they can, because there's d orbitals available for bonding. Let's think about the third shell. In the third shell, you have a 3s2. If you fill that up, you have a 3p6, and you have a 3d10. That's a total of 18 electrons that you can put in the third shell. So those atoms that have their outermost electrons in the third shell, they have orbitals that can accommodate an excess of 8 electrons, like SF6. We have 2, 4, 6, 8, 10, 12 valence electrons around the central atom. Now, I did not include the lone pairs here for the fluorines. I'm just trying to show you that silicon, SF6, can have an excess of an octet. Phosphorus is also in the third period, which means it can exceed the octet rule. So we can have something like PCl5. We've got 2, 4, 6, 8, 10 valence electrons around phosphorus there. So if you'd like to stop the video and try these on your own, give it a shot, or you can watch me do these. Now I'm going to do these structures. I'm going to draw these lower structures using the alternative method, something closer to what you've probably seen in general chemistry. So go ahead and pause the video, try them on your own. And once you've tried these, we can look at my solution. All right, so step 1, if we're looking at NH3, we're going to add up our valence electrons by looking at the group number. So that's 5 plus 3 times 1 is 3. So we have 8 electrons to use. Our central atom is going to be nitrogen because hydrogen can never go in the center. Step 3 is we want to distribute the remaining electrons to the exterior atoms. Now here's the thing, hydrogen can't exceed 2 electrons. So the hydrogens already have 2. Do not put any more electrons on hydrogen. So now we're on step 4, in which we put any extra electrons on the central. So look, I have 8 to use, and how many have I used so far? 2, 4, and 6. I've got 2 extra electrons. Step 4 says we put them on the central atom. Now we check to make sure each of the atoms is happy. And it is. Nitrogen has 2, 4, 6, 8. Hydrogen has its 2 electrons, so this structure is good. Let's look at the next one, C2 or CH2O. So carbon has 4 electrons. We have 2 of the hydrogens, so 1 valence electron each. Oxygen has 6 valence electrons, so that gives me 12 electrons to use. My central atom, step 2, should be carbon. Remember, hydrogen is never in the center. And carbon is less electronegative than oxygen. If you need to pause the tape, pause the video, and look at your periodic table, do that. Step 2 says we want to put our exterior atoms attached to the central atom with a single bond. Step 3 is we're going to distribute the remaining electrons to the exterior atoms, the atoms on the outside, not the central. So hydrogen doesn't get any more. We're going to give oxygen the octet. Okay. And right now I'm going to count. How many did I use? 2, 4, 6, 8, 10, 12. So after step 3, I've distributed all of the electrons. Step 4 says put any extras on the central. Well, I don't have any extra electrons. So let's go to step 5. Step 5 says if your central atom does not have an octet, you're going to need to use multiple bonds to do that. So here's the thing. Carbon cannot borrow any electrons from hydrogen. But carbon can borrow a pair of electrons from oxygen. So let's get rid of that pair. Carbon says, hey, oxygen, can I borrow a pair of electrons? And oxygen says, sure, let's share. So we get rid of the lone pair and turn it into a bonded pair. For C2H2, we add upper valence electrons, so 2 times 4 plus 2 times 1, that gives me 10 electrons. Now let's look at carbon, which we know one of them has to be the central atom. And this kind of, you can treat one of the carbons as your central atom. And because I only have 2 hydrogens, let's distribute these symmetrically. And now let's add our electrons in. I have 10, I've used 2, 4, 6. So remember, let's treat this carbon as the central, and everything else is the exterior. Hydrogens are not getting any extra electrons. 2, 4, 6, 8, 10. All right, that's step 3. Step 4 says put any extras on the central, which we don't have any extras. Step 5 is if your central atom does not have an octet, then you're going to have to use multiple bonds. So carbon can share that pair, and it can share that pair. Now each atom is happy. Our final example here, let's add up our valence electrons. 4 plus 3 plus 6 plus 1 gives 14 electrons. Carbon is going to be your central atom. Now, if we attach everything to the outside of carbon here, we notice that we have an extra hydrogen. So we can't put any more bonds to carbon, so let's put it to oxygen. If I distribute the remaining electrons to the exterior atoms, I see there's only one place I can put them, that's on your oxygen. And I notice that I've used all of my electrons, 2, 4, 6, 8, 10, 12, 14. So there's your structure. If you need more examples of this, there's tons of videos on YouTube, or you can reach out to me and I can give you some additional practice that you could use to supplement the homework problems. Section 1.4 deals with formal charges. Recall the terms we use to describe an unbalanced or formal charge. So an anion is an atom with a negative charge. A cation is a positively charged atom. Anions result from gaining electrons. Cations result from losing electrons. So atoms can be neutral, but they can also be anionic or cationic, and we need a way to sort of denote this and show the reader what's going on with the charge. So atoms that have gained or lost electrons, right, that are not involved in ionic bonds, we're talking covalent bonding in molecules now, we use formal charges. This is different from what you learned about charges in Chem 1. Now, sure, it sort of means the same thing, but it shows an excess or deficiency of a valence electron. However, we're dealing with covalent bonds now. So we have something a little different. The sum of your formal charges should equal the total charge in the molecule. So we're going to check our formal charges on each atom and make sure that they match the formal charge on the particle. So there are several ways to calculate the formal charge. I particularly like my method. The book outlines something a little different. If you look online, there's also a lot of different ways to do this. I'm going to show you the easiest way to calculate the formal charge. So if we use this formula, the formal charge equals the number of valence electrons, remember that's your group number, minus the number of electrons owned by that atom, and I'll show you how to do that. So when we determine the number of electrons owned, you're going to give one electron from each shared pair to each atom in the bond. So let's take a look at ammonia, NH4+, and let's calculate the formal charges for each atom. Now, I draw the Lewis structure. Step 1, you can't do formal charges unless you have a correct Lewis structure. You draw your Lewis structure. Remember, each single bond represents a sharing of 2 electrons. So if you'd like, you can draw the electrons in now. This might be helpful to determine the number of electrons owned. Let's first calculate the formal charge on each of the hydrogens. So remember, formal charge is the number of valence electrons, which is the group number. Hydrogen is group 1, minus the number of electrons that it owns. So if you look, the number of electrons owned, you're going to give 1 electron from each shared pair to the atom in the bond. So let's look at this hydrogen here. There's 2 electrons shared between the hydrogen and the nitrogen, but we're going to give 1 to that hydrogen from that bond and 1 to the nitrogen in that bond. So it looks like this hydrogen owns 1 of those electrons. So 1 minus 1 is 0. For nitrogen, we take our group number, 5, and now let's look. Nitrogen had 4 bonds, so if we give 1 of the electrons from each of those bonds to nitrogen, we see that nitrogen owns 4 electrons. The formal charge on nitrogen is 5 minus 4 equals a plus 1. Now let's total them up. The hydrogens each had a formal charge of 0, 0, 0, 0, and our nitrogen was plus 1. So let's check to make sure that the sum of the formal charges equals the total charge on the particle, which it does, plus 1. So we know we've assigned our formal charges correctly. The reason we're doing these formal charges is because it's going to help us to understand the reactive sites on a molecule down the road. So there's a reason for this, but we need these basic skills first. So what I'd like you to do is pause the video and try each of these on your own, calculating the formal charges on each atom, and then checking to make sure that they sum up to equal the charge on the particle. So if you want to calculate the formal charge on NO3, that's the nitrate ion, you first need to draw a Lewis structure. So this is the Lewis structure for nitrate. And let's do the formal charge on this oxygen. So oxygen is group 6 minus, now how many electrons does it own? Well, in this bond, let's give one to oxygen and we'll give that one to nitrogen. So let's focus here on oxygen. It owns 1, 2, 3, 4, 5, 6, 7. So the formal charge on that oxygen is -1. And this oxygen has the same bonding pattern here as this oxygen on the right. So we have a -1 formal charge for both of those oxygens. Let's look at the oxygen up top. The formal charge is going to be group 6 minus the number of electrons that it owns. Now, here's something different. We have a double bond. So a double bond means there's 4 electrons being shared. So let's give 2 to oxygen and 2 to nitrogen. Let me do this one. So now we've got an oxygen that owns 2, 4, 6, has a 0 formal charge. Notice this fits perfect with our bonding patterns that we learned earlier. An oxygen that has 2 covalent bonds and 2 lone pairs is neutral. All right, finally, let's look at our nitrogen. We have a group number 5 minus, now if we look at how many it owns 4, giving us a formal charge of +1. So does the sum of the formal charges equal the charge in the particle? I have -1, -1 plus 1, that equals a -1, which it does equal the charge in the particle. Moving along to H2O, draw your Lewis structure. For hydrogen, your formal charge is going to equal group 1 minus, if we give the hydrogen 1 and the oxygen 1, so now hydrogen owns 1 electron, 0. If we look at the other hydrogen, we have the same bonding pattern, so we have a 0 formal charge on both of these. Now let's look at our oxygen. The formal charge is going to be group 6 minus the number of electrons that it owns. It owns 2, 4, 6 with a formal charge of 0. So the sum of the formal charges is 0, which is equal to the charge on the particle. Our final example, we have C3O minus. We draw our Lewis structure, or CH3O minus, sorry. We draw the Lewis structure. Formal charge on each of the hydrogens is going to be the same because they have the same bonding pattern. Hydrogen is group 1. Now if we break these bonds and give 1 to hydrogen, 1 to carbon. I'm just going to break all of my single bonds while I'm at it. Let's focus on one of our hydrogens. Group 1 minus 1 electron that it owns is 0. If we look at the oxygen, the formal charge is group 6 minus oxygen owns 2, 4, 6, 7, -1. And for a carbon, the formal charge is going to equal group 4 minus, it owns 4, that equals 0. Section 1.5 deals with polar covalent bonds. Now, this is where electronegativity becomes very, very important. Make sure you have a periodic table with the electronegativity values in front of you. You will be given a periodic table with electronegativity values on the test. You don't have to memorize these values, but if you know the general trend for electronegativity, that's usually enough to get you through these problems. All right. Covalent bonds can be polar or nonpolar. So what does this mean? A nonpolar covalent bond means that the electrons are shared evenly. A polar covalent bond is where one of the atoms attracts electrons more than the other, or it has a stronger pull on the electrons, or it's more electronegative. So electronegativity is how strongly a particular atom will attract a pair of shared electrons. And the trend is up and to the right. Fluorine being the most electronegative atom on the periodic table. There are three types of bonds that you've probably seen in general chemistry. Covalent bonds, now we have polar covalent bonds, and ionic bonds. A nonpolar covalent bond remember we said is where the electrons are shared evenly. We can characterize this by looking at electronegativity difference that is less than 0.5. So carbon, each carbon is 2.5. If you look on the table, each carbon has a value of 2.5. 2.5 minus 2.5 gives you a difference of 0. So it's less than 0.5, therefore it's nonpolar covalent. Carbon 2.5, if you look at the value on your table for hydrogen, it's 2.1. Just take the absolute value of their difference and you get 0.4. 0.4 is less than 0.5. So a carbon-hydrogen bond is nonpolar. All right. Here's something you just need to know. All carbon-carbon bonds are nonpolar. All carbon-hydrogen bonds are nonpolar. If you know these two in particular, it's going to save you a lot of time down the road when we're determining if a molecule is polar. Because here we're dealing with bond polarity between two atoms. We're going to be very shortly, we're going to be looking at molecular polarity, and we have to consider all of the bonds. So if you know these two, it's going to make your life a little bit easier when we get there. Polar covalent bonds, remember, are where the electrons are shared unevenly, and the electronegativity difference is going to be in the ballpark of 0.5 to 1.7. Now there are exceptions here, but just remember, a covalent bond is when two nonmetals are bonded, and an ionic bond is where we have metals and nonmetals. So let's focus on the polar covalent bonds. The electronegativity of carbon is 2.5. The electronegativity of oxygen is 3.5. The difference is 1.0. So that falls in between 0.5 and 1.7. Therefore, it is a polar covalent bond. And ionic bonds result when we have an electronegativity difference greater than 1.7. So if you do the math, you can calculate the difference, and we see that an ionic bond with such a high electronegativity difference, right, results in the transfer of one of those electrons. When one of the atoms has such a strong pull, like oxygen, it pulls the electron from the atom that has a lower electronegativity, in this case, sodium. So electrons tend to shift away from the lower electronegativity atom. Remember, the definition of electronegativity is the ability to attract an electron or how strongly an atom attracts electrons. So more electronegative atoms have a stronger pull. Very important, the greater the difference in electronegativity, the more polar the bond. So if you haven't picked up on that trend, there it is. And here's a summary of the values. Make sure that you have a good grip on the characteristics of a nonpolar covalent, a polar covalent, and an ionic bond. Next, we're going to talk about how we represent polar covalent bonds and some of the terminology involved. So, by nature, a polar covalent bond has one of the electrons being pulled towards the more electronegative atom. We have a special word for this, pull on the electrons. It's called induction. And induction is simply the withdrawal of electrons toward the more electronegative atom. It results in the formation of a partial positive and a partial negative. Now, this is different than something like in an ionic bond. In an ionic bond, like Na and Cl, the sodium has lost an electron, the chloride has gained an electron. These have full formal charges. They're not partial. It's a whole electron is transferred. But when we have atoms sharing electrons and they're not transferred, we just have a pull towards one of the atoms more so than the other, we use partial charges. So partial charges we're going to use to represent polar covalent bonds. Very important. Partial charges get the Greek symbol delta, and a delta plus is for the less electronegative atom in that polar bond, and a delta minus is for the more electronegative atom in the polar bond. So the first way that we represent polar covalent bonds is by using partial charges. Delta plus and delta minus, make sure you know where the plus and minus go. Plus on the less electronegative, minus on the more electronegative. The second way we can represent a polar covalent bond is by using something called a dipole moment, a bond dipole moment. This is going to be different than a molecular dipole moment when we get there, but for now, you need to know that a bond dipole moment is simply a vector, right? That's an arrow with direction and magnitude that points towards the more electronegative atom. So, if you look at our example, carbon is 2.5, oxygen was 3.5. If we want to draw the bond dipole moment, we draw this sort of an arrow with a cross, and an easy way to remember this, that kind of looks like a plus sign. Well, that goes on the less electronegative atom. The arrow is pointing towards the more electronegative atom. In our next example, I'd like you to try to do this problem on your own, identify all the polar bonds, identify the partial charges, and the bond dipole moments that result from the inductive effects. So pause the video, give this a shot, and when you're done, come back and see if you got them right. All right, so in our first molecule, we notice we have a carbon-oxygen bond, and we know that the carbon-oxygen bond has an electronegativity difference greater than 0.5. Carbon's 2.5, oxygen's 3.5, a difference of 1. So we know that's a polar bond. We can put our partial charge on carbon, less electronegative, partial negative on oxygen, more electronegative. And we draw that bond dipole moment in, pointing towards the more electronegative atom. We also notice the oxygen-hydrogen bond is a polar bond, so we put our partial positive on the less electronegative. The oxygen already has the delta negative. We draw our bond dipole moment in, pointing towards the more electronegative atom. In the next example, we have four carbon oxygen bonds, all of which are polar. So let's put our partial charges in the correct places. Dipole moment there. The next polar bond here, we have, hold on, that should be a partial minus. Partial positive on the carbon, partial negative on the oxygen. Draw that dipole moment in. On the right side of the molecule, we have two more carbon-oxygen bonds, partial minus on the oxygen, delta plus on your carbons, and we draw our dipole moments in, pointing towards the more electronegative atom. In the bottom left, the carbon-hydrogen bonds are not polar, but the carbon-fluorine bond is. Fluorine gets the delta minus, carbon gets the delta plus. Dipole moment pointing towards the more electronegative fluorine. And the carbon-chlorine bond is just on the verge of being a polar bond, so we have a delta minus on the more electronegative chlorine, delta plus on the carbon. And we draw our dipole moment pointing towards the chlorine. In the bottom center here, we have one polar covalent bond. That's the carbon-oxygen double bond. We know that carbon and oxygen form polar bonds with the electronegativity difference of 1. So our delta minus goes on the more electronegative oxygen, delta plus goes on the more electronegative carbon, and we draw our dipole moment pointing toward the oxygen. Our final molecule, we have several polar bonds here. We have a carbon-oxygen, delta minus, delta plus. We have a carbon-chlorine, delta minus, delta plus. And we have a carbon-nitrogen. Nitrogen is more electronegative than carbon, so delta minus, with our dipole moment pointing towards the nitrogen.